Yeah, awesome. Anyone message me in chat if you want to volunteer to just fill in the boxes here for the multiplication, and then we'll combine like terms. So, anyone want to volunteer for that? Anyone volunteer for these boxes?
Did you just want us to put the answer to the multiplication in it?
Yeah, just say the answers, and then we'll group them all together.
Okay. I'll do one then.
Go for it. Battery's low. Oh, hang on. Give me 1 second. Okay. Yeah, go ahead. Just want to read the first row?
The first row?
Yeah, go for it.
Okay, so x times x squared is going to be x to the third.
Awesome.
X times 2xy would be 3x squared y, right?
This one would just be 2x squared. It just bumps up. The two stays.
2x squared y.
But I know it's going to happen. You're correct.
And then xy squared.
Awesome. And then, do you want to do the rest, the second row?
Yeah, so the second row is x squared y.
Good.
And then the second box is 2xy squared.
Awesome.
And then the last one is y cubed.
Excellent. Thank you. Okay, and then do you guys see that we can we can group together like terms, and like terms are terms that have exactly the same number of x's and the same number of y's. So these terms have an x and two y's, and the green ones have two x's and one y in the exponent. So grouping them all together, what we're left with is this equals to x cubed plus 3x squared y plus 3x y squared plus y to the third. And so you could do the same approach here. You could make another box. You could do x plus y. Or sorry, xy. This is xy, but let me do it like this. xy, and then on the top, you can do what we just had there. You can copy and paste. Copy, paste. And you can do a similar thing with this one. And if you do it all out, this was going to be x to the fourth. This is going to be 3x to the third y. This is 3x squared y squared. This one is, oh, this is y to the third. This is x y to the third. And going here, you have x to the third y. And then you have 3x squared y squared, 3x y to the third, and then the last one is y to the fourth. And you'll notice another pattern here. We've got some similar terms here, some similar terms over here, and some similar terms over here. So combining everything, what you're left with is x to the fourth plus the x cubed y terms combined. You get 3 from the top and 1 from the bottom, so you get 3x to the third y plus 6x squared y squared plus 4x y to the third plus y to the fourth. All right. Nice. I see a few students. Well done, Kieran, Penelope. Well done. So that's just to kind of go to the next step. Would you guys want to do this approach for x plus y to the 6th or x plus y to the 7th? What's like a pitfall of this approach? Go ahead. Nice. It takes a long time. It takes a lot of space. Quentin likes this. Hey, I do believe every approach has a lot of value, even the long approach sometimes. So I'm not saying it's a bad approach. I'm not saying it's a necessarily, but this might take some time. This might not be the most efficient approach. The other thing to be aware of is to get x plus y to the 7th, doing it this way, you need to also find x plus y to the 6th. And to get that one, you need to find x plus y to the 5th, and so forth. So you can't just directly jump into it and do x plus y to the 7th. So this is where the binomial theorem comes in. And we're about to get there. So instead of trying to FOIL everything out, maybe we can kind of look at and see if we find any patterns that are happening here and try to justify why that pattern happens. So does anyone notice any patterns about the terms that end up, by the way, this is called x plus y is a term with 2 letters, so it's a binomial. So this is called a binomial expansion. This is a binomial. And it's a binomial raised to a certain exponent. And when you expand the exponent, you get the binomial expansion. This is the binomial expansion. It just means FOILing powers of x plus y. So what are some observations we can make in, let's say, x plus y to the 4th? What are the terms? What can we say? What do they have in common?
Are you just asking for like patterns in the way it grows, or?
Just the last, let's say x plus y to the 4th. Not necessarily in the way it grows, but just that it's specific thing. What can we say about each term? What's something they all share in common? Alex, what did you say? Yeah, the exponents, does everyone see that? The exponents always add up to 4. There's always going to be 4 letters. And does that make sense why? Well, how can we explain why there's always going to be 4 letters in each term?
Everything's been multiplied by something else 4 times.
Exactly. It comes from x plus y, x plus y, x plus y. So each term, each type of term, x plus y, x plus y, x plus y, x plus y. Each type of term, when you FOIL everything out, comes from selecting some random group of one letter from each set of parentheses. So this would, for example, get you to the specific term y, x, y, y. So for example, if you're doing the expansion of x plus y to the 4th, there's never going to be a term with just like x squared floating around. You have to use all 4 letters. So okay, that's nice. So what that tells us is the types of terms that we have are things that have to have, for example, if we did x plus y to the 5th, let's try to do x plus y to the 5th directly. So x plus y to the 5th. We know for sure the types of things we're going to have always have 5 letters. So we can either have x to the 5th, Or we can have x to the fourth y to the 1, and I'll just write it like that. Or I'm going to leave a little blank here. Or I can have 3 x's and 2 y's. So I'm just counting down from my exponent. Or I can have 2 x's and 3 y's, but they always have to have 5 letters. Last one here will be, or sorry, two to go. 1x and 4 y's, and the last one is y to the 4th. Okay, and I might cut this and move this down. So now we know why there's certain types of terms. The question now becomes, how about these numbers? 1, the coefficients, 1, 4, 6, 4, 1. Oh, thank you. I made a mistake. My eraser's too big. Okay. So let's think about this term, yx, y. This is equal to, when you combine the exponents, when you write it as an exponent and a product, you write x, y to the 3rd. Is this the only way we can get x, y to the 3rd? Is there any other choices that we can do? What's another way we can do it? What's another, just one more example of x, y to the 3rd that it could show up?
x.
Yeah, you could do, so x plus y, sorry guys. I should just copy that one, but x plus y, x plus y, x plus y. You can also do y, x. This would correspond to, in the expansion, y, x, which would also be x, y to the 3rd. And then, I don't want to go through all of them, but what is this really counting? How many different ways will there be to get x, y to the 3rd when you go through the full expansion? It's just 4 choose 1. Nice one. Because you guys see how it's connected to that Mississippi problem we talked about with 2 letters. It's the number of ways you can choose, a number of words you can rewrite with 1x and 3 y's. So overall, there's going to be 4 choose 1 different ways to write to get x, y to the 3rd. And then how about x squared, y squared? How many ways are there to get x squared, y squared? There's several, right? So for x squared, y squared, you can do, you can write x, y. You can also do x, y. You can do, and these, by the way, correspond to, pick the x first. So the first one would be x. Then you do x. Then I'll just write it out here. X plus y. X plus y. So this corresponds to this one. X, y. So basically, any configuration of 4 letters, 2 of them being x's, 2 of them being y, you can figure out exactly where it comes from in the expansion. And what do we learn? How many ways are there to rearrange 2 x's and 2 y's if you're playing Scrabble? Which technique can we use to count that? Anyone see? Nice, nice one. Yeah, just 4, choose 2. So the total number of ways would be 4, choose 2. You can also alternatively think of this as pick the 2 terms that have, so I'm going to do it here. Pick the 2 terms that have your x, and then the other ones automatically pick a y. Here, pick the 1 term that has the x, and then make the other 3 automatically have y's. So that's the first, the number of ways to get x, y to the third is 4, choose 1. The number of ways to get x squared, y squared is 4, choose 2. Yes, so one nice observation that Alex mentioned here is you could also have done 4, choose 3. And if you remember what we talked about last time, like we talked about how, like, for example, 7, choose 5 is the same as 7, choose 2. Because every time you pick 2, it's like not picking 5. So the number of words that have have 2 x's, yeah, the number of words that have, sorry, the number of words that have 3 x's and 1 y is also going to be 4. And if you look at 4, choose 2, this is 4 times 3 all over 2 times 1, which is equal to 6. Okay. So please hit yes if you're comfortable with why these combinations are showing up as the coefficient in the binomial expansion. We're thinking about, we're anticipating the end result, and we know what type of term needs to show up, and then we're going to cleverly count how many ways there are for that term to show up. And then when you do that, you just end up with a combination. And also, please hit no if you're a little bit shaky why that, a little bit confused, because there's a lot going on here. So a few students are confused. Can anyone volunteer to share kind of where they're a little bit shaky, or what, any line, any step? Or you can just message me in the chat also. But I encourage, if any part that's a little bit unclear, please ask. Okay. Yeah. So don't hesitate to ask, because I know, it could look really confusing if you turned away for a second. Is it 4, choose 2 because there are 2 similar terms in the? Yes. So why is this one 4, choose 2? There's a few ways to think about it. First, you can think of it as, when we talked about combinations, we mentioned last week that combinations is also similar to the Mississippi problem, but with exactly 2 letters. But the way I like to think about it is, rather than focusing it on 2 x's and 2 y's, maybe think about it as 2 no's and 2 yeses, and you have 4 friends. So you have like, you have 4 friends: Alice, Bob, Cindy, Dan, and the number of ways to invite 2 of them to the movie theater. Let's say you invite Alice and Cindy, but Bob and Dan are not invited. The number of ways to do this would correspond to the set Alice and Cindy. And so the number of ways to do this is 4, choose 2.
I had a quick question.
Yes.
I'm just wondering, I'm pretty sure I understand the methodology, and I understand how this applies to the general idea, but I'm wondering why you're using combinations instead of permutations, or if it's possible to use permutations. I hope that makes sense.
A little bit. I do have a, so are you asking, like, why did I use 4, choose 2? Like, why didn't I do 4p2?
Not really. It's kind of hard to I think I get it. It's just, I don't know, part of my, let me think. I'm just a lot more fluent with permutations, so I often find ways to make combination questions start with permutations and then go to combinations. So it might just be my general thought process that's causing me to wonder that sort of thing.
Yeah. I see what you're saying. So permutations are the building block of combinations, because a combination is really a ratio of combinations. There's a permutation in the numerator that doesn't go all the way down, and then the denominator you divide by rearrangements. But now, once you have that idea, we're going to stick with combinations for binomial theorem, because combinations are useful because they help you solve the Mississippi problem. They help you solve the Mississippi problem. The reason they do that is because in the Mississippi problem, there's repeating letters that you want to rearrange. And you want to have the denominator, which is that permutation that cancels out by the repeating numbers. So if you see what we're actually counting, we're just counting a number of ways to make different words with some number of x's and some number of repeating y's. And that's really just combination. And just link it, the other thing that make sure is, Karen, do you feel comfortable with kind of this explanation that the Mississippi problem is also the same as like inviting friends to a movie?
Yeah, I understand the like multiple possibilities of like the same thing, if that makes sense.
Yeah, that's called equivalent formulations, or like one-to-one correspondences between different explanations or different ideas. So rearranging words with repeating letters equal to picking friends to go to a movie with you, where you don't care how they're ordered, which is also equal to the coefficient in the binomial expansion. Because literally what you're doing when you're doing a binomial expansion is you're finding out every single way you can write 4 letters together. And the letters can be X or Y. Okay, so now that we know this, let's continue the pattern without necessarily foiling. How many ways are there? We know, does everyone agree? Please hit yes if you are comfortable that the expansion needs to look like this. There's got to be an x to the 5th, there's got to be an x to the 4th y, there's got to be an x cubed y squared, and so forth. So are you guys comfortable that it has to look like this? Because I can only make words with 5 letters, and I'm only allowed to use x and y. So every possibility is there. Okay, how many ways are there? How many words can you think of that have all x's and 5 of them? Just one. And so what we say there is the convention is usually to count from the number of y's. So I like to write this as 5, but choose no y's. So 0 y's. So that's kind of to fit in with the pattern. But there's only one way to do that. How many words are there that, or what combination can we use to write the number of words that have 4 x's and 1 yes? So one of your friends is going to the movie with you.
Or choose one.
5 choose one. Because we have 5 friends, only one of them is coming with us. And then how about you have 5 friends, and you're going to only invite 2 of them. So that's the 2 y's.
Maybe 5 choose 2.
5 choose 2, awesome. And then hopefully you guys are okay. Next one will be 5 choose 3. And 5 choose 4. And 5 choose 5 for the last one. Okay, please in your notes take a minute to actually calculate these numbers and then put the expression together. So I'm going to write it here, and just confirm that you get the same numbers. And the nice thing about doing these is it's kind of like tenet. You guys, tenet is a palindrome. So these expansions will be a palindrome precisely because of the fact that we talked about yesterday. Picking friends and like picking some friends is not picking others is equivalent to switching yes and no. All right. Please hit yes if you were comfortable with this one, and you got those numbers. And please just unmute yourself, ask me any question if there's anything that's unclear how I got these numbers. Or message me privately also. But I encourage you to just hit the spacebar and ask away. Okay.
Basically,
Yes.
we solved the 5 choose 1, 5 choose 2. That's all we were solving right now, right?
Just, like the from the last step to from the previous step to the current one.
Yeah.
Yeah. All you needed to do was just like, what is 5 choose 1? What is 5 choose 2? What are these actual numbers?
Okay.
And the nice thing is you don't actually need to do that many of them. Like 5 choose 0. Everybody should know that picking nothing out of 5 is only one way to do that. 5 choose 1. That's just the top number. Anything choose 1 is always just the number itself. Choose 2 is not too hard. That's 5, 4 over 2, 1. That comes out to 10. But then the nice thing that you should anticipate is that, well, 5 choose 3 is the same as 5 choose 2. 5 choose 4 is also going to be 5. And 5 choose 5 is just 1. Okay. So that's it. That's the main idea. Do you guys see that we didn't need to do any foiling? We just thought about what we should expect to see, and then how many of each thing we should expect to see, and we were able to do it without foiling. And just to go back here, just to go to x plus y squared, right? Why is the middle coefficient? Can anyone explain why is this 2? What combination does that come from?
1.
2 choose 1.
It's just 2 choose 1. There's there's only 2 ways to invite one friend to a movie theater if you're choosing out of 2 friends. Yes, no, and no, yes. Kieran asked a very good question. Kieran, your question is related to the actual. Your question is actually related to the original Mississippi problem, and that's called. So let me just give some terms here. Give some these numbers combinations. These combinations are also called are also called binomial coefficients. And I'm not gonna, Kieran, I'm not gonna actually answer your question directly, but I'm gonna leave it as a little challenge to think about. This is a very good question. This is a, open question, or say, open question. What about, why do we limit ourselves to x plus y? What about, can we do something similar to x plus y plus z, let's say, to the 5th? What if we added another letter? So that's a great question, and I'll give you a hint. You already know everything you need to know to answer this question. So I'll let you think about that. But binomial refers to just using 2 letters and expanding stuff with 2 letters. Did you just decide to make the 5 choose whatever based on the y's? Or could you do it with either the y's or the x's? Very good question. So I chose to choose it to do it with a number of y's. There's a reason for that. I could have done it with a number of x's, and that's totally fine. But the reason I do it is really, really simple. It just keeps track. Like I like to count from 0 going up. So when you're doing the full expansion, it's nice to just start off with all x's and count down to get more y's. But the coefficient, I like to count from 0 y's up to all y's. But you could have just as well done 5 choose 5, try 5 choose 4, 5 choose 3. But the convention is usually start with 5 choose 0 or n choose 0. Okay, I'm going to write the general formula. Don't be intimidated. It's got another variable in it, which will just be a stand-in for the letter for the exponent. So here's the general formula. And this is called the binomial expansion formula, or the binomial theorem. So x plus y to the n. Because I can't write, I don't know how many things there's going to be. I write something called summation notation, which means add a bunch of things up, add repeatedly that formula that's going to follow the summation symbol. So I add up x to the let me count it like this: k equals 0 to n, x to the n minus k, y to the k, and then n choose k. This formula is not saying anything new that you haven't seen yet. It's just formally expressing the pattern. So we're saying if we want to expand something to the nth power, start off with, and k, the way you read this is k is a dummy variable, and you think of n as like some big number, like n is like 10 or maybe 5 in the example that we worked out. And the summation tells you like, keep applying the expression and count up from the bottom k equals 0, all the way k equals 1, k equals 2, all the way up to k equals n. And so this is the official formula. And if you look at the terms, look at the exponents, you can see what's going on with the exponents, right? When k equals 0, it means you have all x's, x to the n, but you have no y's. And as k jumps up by 1, you drop down the number of x's, and the number of y's goes up by 1. And then you also do the appropriate binomial coefficient by doing n choose k. Don't worry too much about this. You don't really need to master this formula, but I'm just showing it to you so that you've seen it. And I encourage you to spend some time internalizing so that it makes sense. But if you understood why this expansion is what it is, and you understand how to get it, then you actually know everything there is to know about this specific formula. It's just the formal way of describing that pattern. Okay, what you might have seen before is there's another technique to do these expansions using something called Pascal's triangle. And what Pascal's triangle does and it's a really cool mathematical object. What it does is it collects the combinations in a triangle. So 1 choose 0, 2 choose 0, 2 choose 1, 3 choose 0, 3 choose 1. Oh, what's it? That, oh, yeah, my bad. I made a mistake here. 1 choose 1, 2 choose 2, 3 choose 1. So it collects all of the combinations like this, 3, choose 3. 4, choose 0. 4, choose 1. 4, choose 2. 4, choose 3. 4, choose 4. And when you write it out like this, I guess in the very first one it would be 0, choose 0. But when you write out all the expansion like this, actually fill it in with numbers, you get this really nice pattern. You get 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And then the last one that we did was 1, 5, 10, 10, 5, 1. So this is n equals 2, because it has two numbers. Oh, sorry, no. Sorry, my bad. This is the first row, n equals 1. Sometimes they say n equals 0 is just x plus y to the 0 is just number 1. This is n equals 2. This is n equals 3. This is n equals 4. This is n equals 5. There's a lot of beautiful patterns in Pascal's triangle, and that's because it just consists of different combinations. So each row is a sequence of combinations.
So would row 15 be n equals 14 or n equals 15?
So the 15th, well, let me ask, because it's a little ambiguous, what do you mean by the 15th row? Like, if I count now, like if I write n equals 15 right now?
Well, I don't know. Like, on one of our practice problems, it says, like, row 22. Does that count n equals 0, or does it start at n equals 1?
I believe that counts n equals 0.
So that means it would be n equals 21.
Oh, hang on. Let me see. Which is that a question on the test, on the practice?
Yeah,
Yeah.
32.
Let me see 32. The third row term in row 22 of Pascal's triangle.
It should be C, right? And if not, it should be A.
Yeah. So generally, it's the first row is considered 1. Yeah, because it's got to be a triangle, It's got that tip. So it would be the row 22 would be n equals 21.
Okay, got it. Thank you.
Yeah, so for these types of questions, like which row it's in the triangles, is always the type of question that makes me very nervous, because I'm afraid I'm going to be off by one. But you do remember that the zeroth power expansion is the first row. So you're actually starting off with the 0, and then you go n equals 1, n equals 2, and so forth. Okay. Does anyone know a cool pattern in Pascal's triangle that you can just use to generate the next row?
Are you talking about? Oh, sorry.
Go ahead.
Are you
I was
talking
just
about?
saying that, like,
Yeah.
sorry, I'm.
Go ahead.
Oh, I saw that, like, when you add the two diagonal numbers, you can get the one below it.
Awesome.
So, like, yeah.
Yeah,
Sorry
it's like 4. No, very good. So yeah, 4 plus 6. This gives you to 10. Or like 3 and 1. 3 plus 1 gets you to 4, and so forth. So the next row, if you just want to do it without calculating combinations, we can figure out the next row will just be 1, 6, 15, 20, 15, 6, 1. What do you guys think? Is this a great way to do binomial expansion? What if you had to do x plus y to the 9th? Would you want to do it this way? And it's maybe a matter of preference. But what's one disadvantage of using Pascal's triangle to do x plus y to the 9th?
You'd have to
I couldn't hear you there for a second, but I hear you saying something. Basically, to get to the higher rows, you need to do the previous row. But the triangle itself is very beautiful. But the question is why, and this is a question is let's use combinations to express like what did we do? 3. Yeah, it was like we did this one. So let's write it in terms of combinations. So the question is, why is there this property? So this one was 3. Why does 3 choose 2 plus 3 choose 3 equal to 4 choose 3? And for the 4 and 6, let's do that in purple. Why does 4 choose 1 plus 4 choose 2 equal to 10, no, not 10, no, 5 choose 2. And see if you can come up with so the question I have here to think about, and really, I really encourage you to think what is the general pattern here? What is the pattern using, can you express it using combinations? And then why is it true? So this is a very important homework challenge, okay? So really, I want you guys to think about this, and we'll talk about it next time. Is the prompt clear? Like, you don't need to know why this is happening to understand how to expand stuff, but you do need to know why it's happening if you want to use that shortcut, that 2 numbers above add up to the number below. Because we just said that shortcut. I don't know why, like I didn't give you any explanation why that might have to happen. But there's a very, very nice reason for it to happen, and you don't need any fancy math to explain it. But you do have to think about what these combinations represent. And you have to think about picking friends. But anyhow, this is called Pascal's triangle, and it's another way you can do an expansion. But I prefer to make sure that you guys know how to expand things just using good old combinations. I don't encourage you to, write out the triangle and use that. And also, by the way, for the first few rows, like n equals 1, 2, 3, 4, you'll probably after doing a bunch of practice, you'll probably have those memorized. Okay, so let's do a little bit of practice. What we just did with the binomial expansion formula is a really general thing with any 2 terms x and y. And as you know, like from x plus y squared, that's like a really useful thing, or just like a square of a binomial. You can apply that to like x plus 3 squared, so x plus y squared is useful for anything that has a term 2 things added together squared. So it's useful for x plus 3 squared, x minus 5 squared, right? These both have that format for 2x plus y squared. We can use the expansion, just substitute for the appropriate number and expand using the format. So this is going to be x squared plus 9, and then the cross term is 3x, and we got to have 2 of them, so that's just 6x. This is x squared. The last term will be negative 5 squared, so that'll be 25. And then the middle term is minus 5x, but we got to have two of them, so that's minus 10x. And then, can you guys tell me this last term? What is it going to be? This last expression? How does it expand? How does the last term expand? The last expression? If you FOIL it out and use that x plus y, yeah, it would be 2x squared, which would be 4x squared. So you square the first thing. You do double the cross term, so that would be 4xy. Awesome. And then the last term will just be y squared. So the idea is this binomial theorem, while it just seems to be about x plus y, you can make it about x plus a number. You can do x plus 3 times y. You can do, there's a lot of flexibility in it. So let's do an example. Let's expand 3x plus 2y, or let's do 3x minus 2y to the third. This would be a little bit tedious to do all of it, so I'm just going to say find the term with y squared. So I'll give you guys a little bit of time to think about it. I haven't shown you how to do it, but hopefully you can think this through. And I'll give you a little hint. This is really like 3x plus negative 2y. So you want to think of these things. This is like the x, some quantity, and this is like another quantity. Let me see here. I'm getting some good ideas. Karen, do you want to share your idea?
Like what I got, or my okay, I got I actually didn't write it on my paper. I got 36xy squared.
Okay, and then how did you, what was your thought process to get there?
So I kind of thought as like 3x and negative 2y, like I just replaced them with a and b.
Okay, that's good.
Yeah, it kind of confused me.
Yeah, that's exactly what we're doing. We're getting something that looks complicated, and we're just really making it, instead of like x plus y, we're writing a plus b.
And then I thought of the possibility that had to have the y squared term, and that was ab squared.
Nice. And from binomial theorem, how many terms will there be that have ab squared?
3.
Exactly. That's going to be 3 choose 1.
Yeah. Oh yeah, 3 choose 1. Sorry.
Oh, sorry, 3 choose 2, because I like to count the number
Okay.
of b. But yeah, it's the same thing, either way. Okay. And then what do you do from here?
And then I just substituted in x and y for a and b, and then I just solved algebraically.
Wonderful. Beautiful. Yeah, so just plug in, and remember, when you substitute, like you gotta make sure that the coefficient of whatever you're substituting is also raised to that power. Be careful with minus signs; they'll go away if you have an even exponent. They stay if you have a positive, if you have a odd exponent. So this becomes 3 times 3x times negative 2y squared on the outside. So all the numbers that you get, I like to collect all the numbers. I get 9 times 4, which is 36. And then the letters, the variables, will be x, y squared. Okay. You can do this, so you can do this approach just to show you, to do the full expansion. Any questions on this example? Maybe we should have started off with the full expansion just to see how it worked. But the full expansion, if you understand the main theorem with like a plus b or x plus y, the full expansion is just an exercise in substitution. So the full expansion will be a little bit messy. I'll just do a little bit of it. It will be 3x to the third plus 3, and the name of the game here is parentheses. Just parentheses are your best friends. Don't expand anything until you're done with writing it all out. And make sure you're kind of thinking of the 3x and negative 2y as their own thing that you're not mixing with anything until the end. So 3 choose 1, 3x in parentheses squared minus 2y to the 1 plus 3 choose 2, 3x to the first times minus 2y to the third. And then the last one is 3 choose 3, which is just 1. Maybe maybe I shouldn't write that one.
Shouldn't it be to the second, not to the third?
Oh, thank you. The last one will just be negative 2y to the third. Okay. One thing I see with students when they're learning this is you kind of focus on just memorizing a formula versus like understanding like the expansion and understanding that we're adding together different ways to get the types of terms. One common mistake I see is people will like confuse like multiplication and addition in this formula. They'll do stuff like plus here or something like that and miswrite things. Really try to make sure that you're really comfortable that we're adding together different types of terms with being counted multiple times, like grouped together. And that's what will help you understand and kind of retain the formula, retain the pattern. Don't think of it as so much a formula, more of as a method for them, quicker. it's a clever way to foil without actually foiling. Here. Okay. So yeah, this is a good place. It should give you a good amount of groundwork to start approaching the questions in the on the homework. And some of them, yeah. Some of them, like the numbers are a little bit big. So like, for example, if it asks something like this, so let's do one that's similar to the homework. So what is the fifth term and this is a little this is kind of what a student mentioned earlier. This is what a student mentioned earlier about where you should start counting. I think Lacha mentioned this. So the fifth term in the expansion of 2a squared plus, or let's say 2a squared minus 3b to the 7th. Okay. So we could actually just expand this by hand and do all of the terms, but it's not going to ask, it's not asking us for all of them, it's just asking us for the fifth term. So here's a question, and this is where you have to be really careful. How many like b's, or how many, this is again b, so this is like b, and then this is a. What does the fifth term actually look like? How many a's and how many b's are in the fifth term? And remember, the first term is just going to be a to the fifth. So then how many b's, a and b's, will be in the fifth term? Exactly. Nice. So the fifth term, if you're starting with counting down from a to the 7th and b to the 0, the fifth term will have only 4 b's. So it'll be a to the 3rd and b to the 4th.
And that's because in the first term there's 0 b's, right? And you're counting up by 1 b each time.
Exactly. Yeah. So these types of questions I always like. I don't ask too many questions like this. I don't like the ambiguity. And this is just like a little detail that sometimes people ask about. So just to be aware of this, I don't personally ask questions like this. I'll ask questions more like the ones, find the term with y squared. When you get to higher level, like when you get to calculus, they'll actually call that first term as the 0th term. So, it really comes down to what you're talking about and how you're labeling these things. But yeah, generally in the expansion, the first term is the first thing that you see, and that has 0 of the b. And that's, so since you're starting from 0, you're gonna have to adjust for that. So the fifth term will be of the form a cubed b to the fourth, and therefore the coefficient in front will be 7 choose 4. And if this was a test problem, I wouldn't really need you to do much more than write 7 choose 4, especially because I'm not expecting you to do some crazy multiplying, like, yeah, it's pretty big numbers. I wouldn't expect you to multiply these. 2a squared in parentheses to the third, and then minus 3b to the fourth. And then whatever that comes out to, just remember that this becomes, okay, let's just do 7. What's 7 choose 4? Anyone? 7 choose 4, 35, I think? 35 times 8 times a to the 6th. Does anyone know negative 3 to the 4th? That's not a terrible one.
81.
81. And then times b to the 4th. So 35 times 8 times 81, I mean, that's, I wouldn't ask you something like this, but the one thing I do want you to be careful with and make sure you know is like the laws of exponents, and like a power, when you sub it into another power, you're going to, have a squared written 3 times. That means you're going to have a to the 6th. So make sure you do know that those kind of laws. All right. So this should be a really good starting place for finishing up the homework. And I'll also post a practice test, which I think now you guys should be able to ace. When you're doing the practice test, I encourage you to not use your notes. Do as much as you can. If you see a problem that you don't know or don't remember how to do, give yourself at least 10 minutes. Just set a timer. Just say, okay, I'm going to think about it for 10 minutes. Take a break. Maybe don't think about it for an hour or so, and then come back to it. Sometimes coming back to a problem can help a lot. Okay. The test will be a closed notebook. But if you forget some things, I will give some opportunities for test correction after. Okay. Oh, on. Okay, yeah, very good. So why is the fifth term a to the third, b to the fourth, if the first term is okay? So this one is this expression. If we just write them out, this expression is, the first one would be a to the 7th, b to the 0, plus 7 choose 1, a to the 6th, b to the 1, plus, and so you count down, and then the b's go up by 1. So b squared, 7 choose 2, and then plus 7 choose 3, a, b to the 3rd, a to the 5th, a to the 4th, and then the next one will be 7 choose 4, a to the 5th, no, sorry, a to the, counting down with the a's, a to the 3rd, b to the 5th. So it's just going to be the 5th term. 5th, this one is the first. Is that okay? Samantha, can you explain? Yeah, just a weird thing. The first term we usually refer to as just the all A's and no B's. Samantha, can you explain how you got 7? Is it because 2 is squared, and then add 3? Samantha, can you which 7 are you referring to there?
The 7 choose 4. I'm just confused on how you got 7.
Oh, why do I have 7 here?
Yeah.
the reason is because this 7 is my overall expansion. It's this 7. So everything I expand always has to have a total of 7 letters.
Thank you.
In the last one, it was I was expanding, to the 3rd power, so that's why it was always 3 choose something. Okay, there's a lot of cool things that we'll see, a lot of neat things that the binomial theorem will be applied to, and it's good for algebra as well. So if you'll encounter this in your algebra class, it's really useful to know to help understand certain concepts in calculus, and we're going to encounter it later on when we talk about probability. Yeah. So any last questions?
If we're having trouble with some questions in like the first 31
Yep.
questions, can we ask those now or should we come to office hours on Thursday?
Yeah, you guys can ask them now.
Because I was having trouble with 23, 25. Wait, let me check.
23, that's a good one.
Yeah, 23, 25, and 29.
Okay, good. So if any of you have to leave, you're welcome to leave whenever. Now we're just going to go over some of the homework here, and I'm glad you asked about them. I did forget that I didn't assign that to be due. Didn't have a chance to go over this. Okay, 23 is awesome. This is a nice. What I like about all these questions is like some of them are about like picking triangles, some of them are about making words, and others are about like picking friends to go to a movie. But what you start to realize is it's all the same thing. And I really like that idea in math, that like things that seem to be different are really actually the same thing in disguise. So this was a number of paths that can go from A to B and from B to C, but you can only go south and east allowed. So for example, one way to do it is go over 2, go down, go over, go down, go down, go down. So that's one path. The question is, how many are there in total? Did anyone come up with an answer here? Anyone have any ideas?
I broke it into 2 parts.
Uh-huh.
So I thought, like, how many ways can you get from A to B? And then I multiplied that by how many ways you can get from B to C.
Awesome.
Yeah, that's what I was thinking too. And I was thinking like maybe there'd be two paths you could take per block, but then maybe I thought that was wrong because like of corner blocks or something like that, because you can only go down and to the right. So I wasn't really sure. I was confused.
Yes. So okay, you had a good idea. Kieran, how did you go count the number of ways to get from A to B? What's the insight?
So I saw that to get from A to B, for example, you have to go south twice and east twice. And then I just thought of the different, I think it was permutations of AABB, or not AABB, south, south, east, east, yeah.
So you can do south, south, east, east. And then the next one, in this example, it would be south, east, south, east, south, east. But it's not permutation, but how many ways are there to make a 4-letter word with 2 S's and 2 E's?
Yeah. Combinations.
It's combination, right?
Yeah.
So this is 4 choose 2 ways to go from A to B. And then how many ways are there to go from B to C?
6 choose 3.
6 choose 3. And we multiply them, as Lasha suggested, because we want to go from, Lasha and Kieran both suggested this, that you want to go from A to B first. That's some number of ways, and each of those ways you will have another possibility, another choice to make how you get from B to C. That's why we're multiplying, because our configurations our entire path that we're interested in counting hasn't been completed yet. So we keep multiplying until we complete the entire path. And each individual part of the path is its own mini little problem. And I hope you guys agree that the nice thing here is to convert counting these types of paths into words. And if you're ever going from one corner of a square to another corner of a square, like along a lattice, you always have to have, like for example, from A to B, you have to have 2 S's and 2 E's. There's no other way to do it. But just the order, you're allowed to change them. By the way, there is a very interesting way to connect this with, I'm going to write it here. If you tilt one of these pictures, there's a lot of beautiful patterns here, but so if you say you start off at here, how many ways are there to walk to this point? There's just one way. How many ways to walk to this point? How many ways to walk to this point? How many ways to walk to the edge here? You can only starting here, there's only one way to get down there.
Oh.
So I'll let you guys fill out the rest of this, but I think you'll see something neat. And it shouldn't be too surprising, but it's another way to think about it and potentially give a neat explanation of Pascal's triangle. But I'll leave that to you to think about.
How do we know it's 6 choose 3 again?
Well, 6 choose 3. Remember, we're trying to make how many words are there that have 6 letters, 3 of them S's, 3 of them E's. That's like saying if you have 6 friends lined up, how many ways are there to pick 3 of them to go to the movie? Let me see here. Oh. Let me just try. I'm going to try one thing here. How do you do the emoji that's questioning stuff? Is it this one? Oh. Yes. Okay. Anyhow, let me copy and paste that. All right, whatever. I got to figure out how to. It'll be fun to paste emojis in different spots. Lacha, which other one did you have a question about?
25 and 29.
Okay, 25. This was about some college thing. Let's see. She has a list of prerequisites.
Yeah, the question itself was confusing to me, like the way it was written.
Right. So she can do either 2 maths, 1 English. Okay. 5 courses are required for the admission to the college, and at least 1 science.
And are option A, B, C, D, and E different classes as well?
Yeah, but they can be in, like, I got like half of it, but I couldn't figure out how to like do the constraints on this problem because I think I got like the like permutation numbers, I guess. But
Like if you write 5 slots out, for the English, it has to be.
Yeah, English is gone, so that's, we can ignore that, right?
But for the math, it's either one or the other, but not both, right?
Exactly. I think that one is the English or generally, not the math or, because you wouldn't take math 31 and math 32.
Yeah. So, but
So
that means you have 2 options still, but
that's
then
2
we
options.
discount it from the rest.
Right.
And then at least 1 science, so that's 3 options.
So that's where it's interesting, right? You can take 1 science, but as you know, some people take like chemistry and physics. Some people take all 3, biochem and physics.
So you have to take at least 1, and then for the other 2 slots, you can have the other 2 sciences. And option A through E.
I would focus more on the cases. So there's definitely going to be 1 math. So we know for sure there's an overall factor of 2. So math 1 or math 2. But what are the overall cases you can do? So the case is if you take 1 science, if you take 2 science classes, you can do 2 science classes, or you can do 3 science classes. If you do 1 science class, how many options are there for the science class you pick?
3.
3. You choose 1. If you do, and you have to do at least 1, so that's where you start. How many ways are there to do the 2 science classes?
3
3.
choose 2.
You choose 2 also. And then the 3, if you do all 3, there's only 1 way to do that. You just got to do all 3.
Yeah.
Okay. Now in each case, each of those cases, what about the electives or the others? So if you took 1 science class, how many electives do you have?
5 choose 2.
Yes, that's right. Because you already took a math, you already took an English, and you took 1 science, so you have 5 choose 2. Here, if you're taking 2 science, that'll take up one of your electives, so you have 5 choose 1. And I don't think it wasn't like an elective was a requirement. So
No,
you
it
can
wasn't.
you can just focus on all science and math and English. You're not taking like, basket weaving or something. Okay, so what we do is should we multiply or add these?
Add.
Which ones?
Good question. Yeah. So some of them we want to multiply across to give us like the completed schedule. This is a completed schedule.
And then add the cases.
And then add the different cases. So this is a completed schedule. So we multiply this, add them all together, and then at the end you can multiply by 2, because in each case you can do math 1 or math 2. Okay.
Will you multiply the whole thing after it's added by 2?
You can either multiply it by 2 at each step or the whole at the end. Everything has a factor of 2.
Okay. So like in the case of case 1, you'd have 3 options for science and 5 times 4, 10 options for the electives?
Yeah. Let's write that. 2 times 3 times 1 times 5 choose 2 plus 2 times 3 choose 2 times 5 choose 1 plus 2 times 3 choose 3 times 5 choose 2. And I can calculate what that comes out to. That's 2 times 3 times 10 plus 2 times 3 times 5 plus 2, which is, this would be 60 plus 30 plus 2, 92.
And does that work if you multiply the whole thing by 2 at the very end, or no?
Yeah, because everything has a 2 in it.
so it'd be like 30 plus 15 plus 2.
Plus 1.
Oh, plus 30 plus 15 plus 1 times 2.
Yes.
Okay.
Yes. And then
And yeah, okay.
what was the next one? Oh, yeah. You had a question about that?
We're also like we're not showing it, but we're also multiplying everything by 1 for the 1 English class that we're taking.
That's correct. I'm not writing it down, but technically everything is being multiplied by 1, choose 1.
Okay, cool.
Exactly.
Let me just take a picture of this.
I'll post this as well.
Cool. And what about 29?
Mm-hmm. The next class I'm going to ask you guys a problem that I saw that stumped me for a little bit. That reminds me of this one about books on the shelf, but not about combinations. That's how many ways can 8 books be arranged so that books on biology, history, and programming are never together? Anyone have any thoughts on how to approach this?
Well, I mean, you can start with 8 factorial because you know you're going to have to subtract options off of that. And like I found when you did, like how we did the cars problem where we did 7 factorial and then subtracted those restrictions off of the original. So I know that it's, but like I just don't know how to do when there's spaces in between. I guess is all I'm saying.
Does this mean that the 3 subjects, what were they? Biology, history, and programming, all 3 of them can't be together, or 2 of them can't be together? That's what I was confused about. Like, can biology and history to be together if programming is somewhere else? Or does it mean if any of them are next to each other, no matter in what arrangement, it's a no-go?
It's if any of them, because when you do some of them, it's not an option.
Let's see. Yeah. So, Alex, so you're saying, so what? That's a question that Lacha, that example that he gave, like let's say biology, history, but programming somewhere else. Is that considered together, or is that allowed?
Yeah, that's my question. Like, yeah.
So
I think in this specific question, it might mean that if any of the 3 are together at all, it's not okay. But what in the wording like tells us that?
It says
yeah, go ahead, Alex.
it says or instead of and.
Oh yeah, okay, cool.
Is it-
Biology, history, or programming, not biology, history, and programming.
Yeah, so there's a little bit of you have to think about
It's
the logic
ambiguous.
of them. Yeah, I think it is the difference between or and there, but either way. So Alex, how did you set it up? But it sounds like you had a good solution.
Oh, well, I haven't solved it yet because I don't know how to do when they're like not like together, I guess.
Oh, but how about like the thing with the superletter?
Yeah, so I mean, I've gotten to where I've subtracted 8 factorial,
Mm-hmm.
subtracted 6 factorial from 8 factorial because when you have 6 factorial, that gives you the number of cases where all 3 books are together as like 1.
Yes, and so you're really close. So it's not just 6 factorial, because let's say we have biology, history, and programming, and we have, let's say, let's call it X, X, X. How many books are there total? 8? 1, 2, 3. So you have the other books, and we have biology, history, programming, and that is, this is like a super letter. So how many words are there that we can arrange here?
7 factorial?
Uh,
Oh wait. Oh wait, 6 factorial.
it is 6 factorial, but what do we have to also consider?
Oh, that the B, H, and P can be arranged in 3 factorial different ways?
Exactly. So each way to do an arrangement of the x's and the superletter, you can go one layer deeper and say, okay, in that superletter, there's actually 6 different superletters I can have, because I can rearrange the BHP. So this, I would check out this. This would be the answer if they're not all allowed to be together.
But now we have to consider like B and H together, H and P together, and B and P together.
Yeah. So right. So I think Lacha is correct that that case that you mentioned, we don't want to allow that case. So we want to consider cases where. So this is actually something that I didn't talk about. It's called inclusion exclusion. So it's when you're trying to count, and some of the cases that you're removing, they overlap. So let's consider. So here's the idea. If we count the cases with B and H separated. Separated A. Cases with B and H separated, with each of them would be 8 factorial minus 7 factorial
Times 2 factorial.
Times 2 factorial.
Yeah, okay.
Those are the cases with BH separated.
So can we just do that 3 times? Like the 7 factorial, 2 factorial?
Very good. So you have to be careful, because some of the cases where they're separated
are the same because there's 3.
Yeah.
So can you add that back?
Yes. Let's see. What do we have to do here? Let me think about this. Maybe rather than let's instead of let's do it instead of doing separate cases of this. Let's think of words that are together. So yeah, exactly. This is on the right track. So here's how you can think about it. And I think you guys are very close. How about I leave you with an idea? So do 8 factorial minus an interesting quantity. Quantity of ways whereas at least 2 books, 2 together. And focus on how to calculate this quantity. So that's what I'll leave you with. And you're very, very close. I think you guys are. Can you get this? The hint I'll give you is if you ever have a Venn diagram, and I think you kind of alluded to this. If you ever have a Venn diagram with 80 in group A and let's say 100 in group B and 20 in the overlap, how many people are in there total? If you add them just together, you're overcounting because you're you're not accounting for the fact that the people in the middle got counted twice. So you want to do 80 plus 100 minus 20, which is 160 total. So this is kind of the start of, yeah, perfect. This would be the start of something called the inclusion-exclusion principle. So you include things, then you exclude things where there's cases overlapping. So I'll leave you to think about this one, but you have the main ideas that could help, and then we can go over it next time. Lasha, did you have any other ones?
That was it till 31. Thank you.
Okay, cool. Yeah, so please remind me about this one next time if you had any questions still.
Thank you.
All right, thank you.
Cool.
Have a good day.
You too. See you guys.
Are we going to have a question like 29 on the test, do you think?
I'm not going to ask about inclusion exclusion. It is cool to see it, like counting things and then subtracting by overcounting. But you'll see in the practice that doesn't come up.
Okay, thank you.
Mm-hmm.
Oh, I had a question about the assignment on Khan Academy. Is that part of the homework that was due on Sunday?
No. So for later assignments, I will ask you to like officially do the Khan Academy stuff, and I'll grade it based on your completion of Khan Academy because I can see like which ones you've done. The Khan Academy thing was just so you kind of get some practice and maybe can do some self-preparation before the class if you wanted to go ahead.
And then when we turn in the rest of the homework on Sunday, do we unsubmit the homework assignment that we turned on this past Sunday so that we could submit the rest? Or will you make like another assignment on Google Classroom for us to turn it in?
A good question. I think I'll just do another assignment.
Oh, all right. Thank you. Appreciate it.
Of course.
Have
See
a
ya.
good day.
You too.